Hello. In this video, we teach you a very important skill to help prove any sort of generalization in a math problem. It's called mathematical induction. Let's get started. So to begin, I wanted to talk about an example that you might already recognize from real life. Let's suppose you're in the dark and you're trying to go up a flight of stairs. If you're like me, you're a little clumsy, and so you want to make sure that this is really going to work. Like, is there really a step in front of me? It's really dark. The idea of induction works that way. Basically, you take one step, that's our base case. You think, okay, that one worked. Let's see if there's another one. And you think to yourself, well, it's now worked for like 10 steps. Surely there's another step because I'm not there yet, right? And so the idea of induction is if it works for the first time and it works for the first, let's say, k times, then surely it should work for the next time. Another real-life example is called the domino effect, and you see that on the slide as well. The idea that if you've ever played with kids and they've never seen it go down before, a domino experiment where you line the dominoes up, it's really fun to watch their reactions. And this is the idea. You basically convince the kid that as soon as you hit one, it's going to hit the next, and eventually it's going to hit all of them, right? And hopefully they'll believe you. But if not, you could do the demonstration, of course. You watch as you allow one domino to fall and it hits the other. So now they at least have that buy-in. Okay, so if you hit one, it hits the next. Okay, so it has a base case. Then you say, well, I'm going to show you that it works for the first 10 dominoes. So they stack up the first 10, it works for the 10th, the 11th goes down. Now, by induction, you could say this works in any situation. As long as you stack up those dominoes, you hit the first one, all of them go down. That's the idea of generalizing something. You see a pattern and you want to prove it. So you find a base case, you say it's working for this small case, I think it works in general, but to prove it, induction says you need to assume it works for the first k times and then show by induction that it works for the next time. And so here we've generalized that for you. Step one is base case. Show that the statement is true for your initial value when n is 1 if you're trying to show it works for all natural numbers, let's say. That's the easy part. Step two is the induction part. With induction, that's where we're going to assume that our statement, our mathematical statement that we're trying to prove, that it works for the first k terms. Now this might be the first k terms of a sequence or the first k terms of some sort of multiplication or other operation. You assume it works for the first k terms. That will be called our induction hypothesis, kind of like a science experiment when you did as a kid. You had a hypothesis. You think this is going to be happening. Right? So our induction hypothesis is when we assume that this statement holds for the first k terms. What that will mean for us is replacing every n with k. Pretty straightforward. Now the hard part is where you really have to be strong in algebra. The hard part is to use that assumption, that induction hypothesis, to show that the statement will work for the next term. Well, what would the next term be? It would be 1 bigger than k, so k plus 1. If you replace your n with k plus 1, you're then going to use some pattern recognition, some substitution, and a whole lot of algebra to legally prove that by induction, your generalized statement holds. At that point, we typically use a triangle of dots, and in math, that triangle of dots is read therefore. So that's just a shorthand. Therefore, the statement has been shown to be proven for all such n, natural numbers n, by mathematical induction. And in the past, we normally would write Q, E, D at the end of our proofs. That meant in Latin, quod erat demonstratum, meaning we have demonstrated or shown that which was to be shown. But nowadays, we've gotten a little bit less into Latin and a little more lazy. So now we use a black box. So that would mean also we've proven it. That's the end of our proof. Okay, so let's go ahead and try a couple proofs today. I would recommend pausing this video as many times as you want because this will seem very unfamiliar. But if by the end of today you go, you know what, that was kind of fun, you don't have to tell anybody, but you might be a mathematician in training. Let's get started. Example 1 says, use mathematical induction to prove the following statement. 1 over 2 times 4, really 8, plus 1 over 4 times 6, plus 1 over 6 times 8, plus dot, 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 and then our nth term, 1 over 2n times 2n plus 2. Okay, so we're adding up the terms of a weird-looking sequence of fractions, and the claim is that that sum, if you stop at the nth term, will equal whatever term number that was, n, over 4 copies of n plus 1. So this is a pattern that someone has discovered, and now they want to prove it. Okay? So by induction, we're going to prove that this generalization holds. The first thing we're going to do is show that it works for a base case. Now, because this is for all natural numbers, it's natural to start counting at 1. So we'll begin with when n is 1. Well, n is 1 is our first term. We already know what that is on the left side. So on the left side, we would have when n is 1, it should just be 1 over 2 times 4. We can see that's the first term clearly, but let's plug it into the generalized term. This is like your nth term, if you will, your generalized term. So the first term, according to the formula there, would be 1 over 2 copies of n, and here is 1 because it's our first term, times parentheses 2 times 1 plus 2. And hopefully you can see what that equals by yourself. The question is, does that equal the right side? If this is truly true, it should work on the left and on the right. It should be the same. So when n is 1, we'd have 1 over, on the right side here, n is on top, so that's our 1. So we'd have 1 over 4 copies of n plus 1. But n is 1, so this is 4 copies of 1 plus 1. Let's see what this is looking like. On the left side, we would have 1 over 2 times 1, but that's just 2. So I would have 1 over 2 times 2 times 1 plus 2. Well, 2 times 1 is 2, and 2 plus 2 is 4. So the left-hand side is really 1 over 2 times 4. Hey, we already knew that. That was our first term. So I was just going through the process so you could see what to do in general. So our first term is, in fact, 1 over 2 times 4. But if I take the right side and replace n with 1, I'm also getting 1 over 4 copies of 2. Well, isn't the same thing on both sides? We have 1 over 8, don't we? So yes, in fact, the statement holds for the first case. Now, if you wanted to show to yourself, hey, this is working for the first 2 terms, for the first 3 terms, feel free to check as many as you like, okay? So you're welcome to create that intuition by checking. And that's what a mathematician would have done. They would have seen, hey, this is working for this many terms. I wonder if I could generalize it. Okay, so we've shown it works once. But how about for the induction step? Well, for the induction step, we first need to create our induction hypothesis. So the way we do that is to assume it's true. Notice we're assuming, we're not showing in this step, we're assuming. Assume it's true for the first k terms. Now, k is just a constant. It could be 10, it could be 100. We're going to keep it generalized, though. We're not going to actually pick a number. So if it were true for the first k terms, I can simply write the statement with n replaced with k. So this would become 1 over 2 times 4 plus 1 over 4 times 6 plus 1 over 6 times 8 plus dot, dot, dot plus 1 over, and here's where the generalized term changes, because now it's not the first n terms, but the first k. So this would be 2 copies of k, so 2k, parentheses 2k plus 2. So I've simply replaced n with k. Now, if that's the sum of the first k terms on the left, then it should also equal the sum of the first k terms on the right. So replacing n with k, you'd have k over 4 copies, that's right, of k plus 1. Now, I usually like to tell myself, this is my induction hypothesis. I need to use this later on in my next step. So I usually like to maybe put a big rectangle around it. I'm very visual, you may or may not be, but I usually tell myself, I'm going to need this later. This is my induction hypothesis. So we're going to use our assumption, the induction hypothesis, to prove the next and final step. So what is that final step? Let's get to it. Our final step of induction is show, and this is where the algebra comes in, that your statement works not just for the first k terms that we assumed, but for the next term, one more than k, which would be k plus 1. So what you do at this step is the tricky part. You actually replace n with k plus 1 in the original statement, and then you have to use pattern recognition in algebra to prove it. So let me show you what I mean. On the left side, for example, we would have the following. We would have 1 over 2 copies of 4 plus 1 over 4 copies of 6 plus 1 over 6 copies of 8 plus dot, dot, dot. I'm going to be a little bit clever here and leave some space if you don't mind. Plus 1 over 2 copies of, and instead of n, I'm writing, that's right, k plus 1 in parentheses. So 2 copies, parentheses, k plus 1, parentheses, now it's supposed to be 2 copies of k and then plus 2. But here, it's not k, it was n, but now it's going to be k plus 1. So carefully, that's 2 copies, parentheses, k plus 1. That was your n that we replaced with k plus 1, and then add 2. Now, I could probably do some simplifying there in a moment, and you might be wondering, why did she leave such a big space there? I'll tell you in a moment, I promise. Now, the question is, does that equal the right side? The right side of what? Of the original statement when n is k plus 1. So what would the right side have been? Well, the numerator would have been k plus 1, since that was n, and the denominator would have been 4 copies of k plus 1 plus 1. But isn't that really k plus 2? So that's what we're trying to show, that the left side equals the right side. I'm going to put it in another box so we can remind ourselves that's the goal. We need to show that the left side equals that right side when n is k plus 1. Now here's where I want to point out why I left that blank where it was. Because right before the k plus 1 term, what term would be right before it? Well, it'd be one less than it, wouldn't it? It would be the kth term. So what was the kth term? That's right, the kth term was this term right up here. It was 1 over 2k, so replacing n with k, times parentheses 2k plus 2. Okay, that's a lot of writing. You might be a little annoyed right now. Most students are. It's okay. So what does this mean? Well, this is saying we now have on the left side that the sum of the first k plus 1 terms should equal k plus 1 over 4 times k plus 2 on the right. So how do we prove it? That's the question. So notice I put a little question mark to tell my reader I have to show that this is true. Okay, so what do we know? Well, we assumed in our previous part of this induction step, we assumed that we knew the sum of the first k terms because of the pattern, right? We assumed that the sum of these first k terms, which is what this is the sum of the first k terms. We assumed we knew what that was, right? The sum of the first k terms should equal k over 4 copies of k plus 1. So I make my substitution. Here's where I substitute my induction hypothesis. So what does that mean? On the left side, I now have k over 4 copies of k plus 1. So that's this part here. And then right next to it, I have to copy what I had on the right of it, which was the k plus 1 term. This was the k plus 1 term. So I need to actually copy that. That would be plus 1 over, let's see if we can clean it up a little bit. So I had 2 copies of k plus 1 in the denominator. But if I were to distribute and combine like terms, we'd have 2k plus 2 plus another 2. Well, that's 2k plus 4, isn't it? And there's a little bit more algebra that we can do to make this easier for ourselves. For example, do you see a common factor in the two terms 2k and 4? Yeah, 2. So if I factored out the 2 that they shared, what would this become? That's right, you'd have a 2 times a k plus 2. So if you cleaned that up, what would happen? Well, you'd have 2 copies of 2, and you multiply them since they're all touching. 2 copies of 2, that's really 4. And then you would have k plus 1 next to it and k plus 2. Well, let me go ahead and do some erasing if you don't mind. Feel free to pause it if you need to write that down right now. But I would really have 4 copies of k plus 1, k plus 2 in the denominator. So let me clean that up real fast. That becomes, where's my pen? There he is. Our numerator of 1 and our denominator has 4 copies of k plus 1, k plus 2 after simplifying. So here I just simplified if you're curious later as to what your professor just did. You can always go back and watch me do it again. Okay, this is back to intermediate algebra, or your previous algebra classes, where you were asked to add 2 fractions. We always needed a common denominator. And since we have 4 copies of k plus 1 in the first denominator, we would have said that our LCD, our least common denominator, would need all of the first denominator, so 4 copies of k plus 1. But it would also need anything new in the second denominator. So that's that k plus 2, isn't it? So that's our least common denominator. I'll come back and clean that up since you can't probably see it too well right now. So that's going to be 4 copies of k plus 1, k plus 2. So I'll rewrite it here. 4 copies of k plus 1, k plus 2. But how did we get that? Well, we would have had to multiply each fraction by whatever it's missing in the denominator to have the full LCD. So we'd say in the first case, for example, this k here, it needed to get multiplied by something. By what? Well, what was it missing? It was missing k plus 2, wasn't it? What about the second fraction? Well, it had the entire denominator already, so I can simply copy the plus 1 as my numerator. Finally, you're almost done. Now it comes to, can you distribute, can you factor, and can you cancel? So let's do a quick distribution. K squared plus 2k plus 1 would be our numerator there. K squared plus 2k plus 1 over 4 copies of k plus 1, k plus 2. I know it's a little tedious, a lot tedious. The question is, does that equal the right-hand side? And we have it in the box here. Does that truly equal the right-hand side? Well, can you factor k squared plus 2k plus 1? Take a moment. Feel free to pause the video. That's right. That's k plus 1, isn't it? Well, what can we do next? Well, yeah, we can cancel. So if we cancel correctly, we would have death to you, death to you. We would just have k plus 1 on top and 4 copies of k plus 2 on the bottom. In fact, that is the right-hand side. We usually abbreviate RHS for right-hand side. So we've now shown that the left-hand side of the statement equals the right-hand side. Therefore, this statement is true for all natural numbers n by induction. So that is an example, and there's a little box or QED, of a proof by induction. I know it was very tedious and that was hard to probably follow. So feel free to pause it, watch this part of the video again and again before you go to your next example, where I'm going to ask you to try it on your own first by using this one as your demonstration. Okay. All right, so hopefully you looked at that other example from the video a lot and you really understand the 3 steps. And now we're going to jump into our last example. And in this last example, see if you can pause it and do it yourself. So it says, use mathematical induction to prove that 5 plus 25 plus 125 plus ... 5 to the n does in fact equal the other side of 5 copies of 5 to the n minus 1 all over 4. So again, this is my recommendation. You pause it, you try it yourself. Okay. Assuming you've done that, let's get started. So we're going to assume that we know the steps here, right? We know that the first thing we need to do is show that this statement holds for at least a base case, for at least n equals 1. So what would that look like? Well, that would be our first term. We know the first term is 5, but we could also see it using the general term 5 to the n, right? On the left-hand side, I'll use my abbreviation here, LHS. On the left-hand side, we would have 5 to the 1. The question is, does that equal the right-hand side? Well, what is the right-hand side? It's supposed to be 5 copies of 5 to the n, where n is 1, minus 1, all over 4. Okay, well, what does that mean? We know 5 to the 1 is 5, so that's the left-hand side. Let's see if it equals the right-hand side. We would have 5 copies of 5 to the 1 is 5, 5 minus 1 is 4. So I would have 5 copies of 4 divided by 4. Well, that's cute. The 4's cancel. And yes, 5 equals 5. In other words, 20 over 4 is 5, right? Okay, so you've showed the base case. Wonderful. Now the induction begins. We start off again by saying, let's assume it works for the first k terms. What did that mean again? That's right. Write out your statement, but with n equals k. So this would be our induction hypothesis that 5 plus 25 plus 125 all the way out until we add the kth term. So 5 to the n is now k, good. We're assuming it's true that this side on the left equals this side on the right, where n is now k. 5 copies of 5 to the k minus 1 all over 4. Now, a lot of students get a little lazy when doing these proofs. Try to avoid that temptation. You do need to write out the entire induction hypothesis. Okay, so the reader understands what you're actually doing, the entire sum here. So this is your induction hypothesis. We are claiming, or assuming I should say, that if we take the first k terms and apply the trick, it works, right? So this is our induction hypothesis. What do we have to do now to show that this is really a true generalization? By induction, we need to show it works for the next term. So let's go ahead and do that. What is the next term? It's when n equals k plus 1. So the left-hand side would have been what? Well, if n equals k plus 1, that would have been 5 plus 25 plus 125, all the way out to what term? That's right, to the k plus 1 term, which is technically out here 5 to the k plus 1. But who comes right before the k plus 1 term? That's right, the kth term. 5 to the k is right there. So that's the implication you have to recognize, that if you're going out to the k plus 1 term, the term right before it is the kth term. Now our job is to show that this is truly equal to, so that's why I write my question mark, because I have to show it. I have to show it. That this is truly equal to the right side. So what is the right-hand side? If n is now k plus 1, the next term, it would have been 5 copies of 5 to the power of k plus 1 minus 1 all over 4. So I like to put it in a little box. I have to show, this is my goal, right? This is my goal. I need to show that the left side equals the right side. So let's begin. What was the next thing that we did after you've rewritten the statement in terms of k plus 1 terms on both sides? That's right, you would recognize that we have the sum of the first k terms present, and so we can replace it with our induction hypothesis. We're claiming by assumption in our previous part of this step that we know the sum of the first k terms, right? 5 plus 25 plus 125 all the way out to 5 to the k can be replaced with 5 copies of, parentheses, 5 to the k minus 1 all over 4. So that's what we're assuming. That's our induction hypothesis. Once you do a few of these proofs, you'll start to recognize the pattern, right? Now the question is, when I add the sum of the first k plus 1 terms, do I get the right-hand side? So the next term is our k plus 1 term, which is 5 to the k plus 1 power. We're going to try to show that it equals the right-hand side using algebra. So here's the rest, just algebra. What do we mean by algebra? Well, we have a fraction plus a number. But any number is really over 1, isn't it? So how could I combine these two fractions now in order to have one single fraction? That's right, we need an LCD, a least common denominator. What would it be? Everything from the first, so 4, and anything new from the second. Well, 1 isn't really new, because if you multiply 4 by 1, you still have 4. So 4 is my LCD, and the entire numerator, the entire first fraction contains it, so we'd have just that numerator, 5 times parentheses, 5 to the k minus 1. But what do I need to do for the second numerator? That's right, I need to multiply by what it's missing in its denominator. So in reality, I have plus 4 copies of 5 to the k plus 1. Now, in order to simplify correctly, you really have to know your algebra tricks. What do I mean? One of the tricks we reviewed earlier in a previous video was that if you had a base b times another base b, so the same base times the same base, with different exponents, how did we combine these bases? Well, that's right, we added the exponents. Notice the base stayed the same. A lot of students want to change it, but this is really saying I have m plus n copies of that base. Notice here why I bring that up to your attention. If you distribute here, you would have 5 to the 1 times 5 to the k. What is that? Well, that's 5 to the 1 plus k, or 5 to the k plus 1. A lot of students incorrectly here will say 25 as their base. Incorrect. The base stayed the same. Okay, so I don't need to reprove that to you, hopefully, but if you need to go back to power rules from previous algebra courses, feel free to do that. What about 5 times negative 1? Well, that's going to be minus 5. And notice here we have plus 4 copies of 5 to the k plus 1 power, and then the whole denominator is just a 4. Can you see how we can go from the left side to the right side? We're almost there. What do we need to do? Well, we need to remember how to combine like terms, right? If you have the same base and the same exponent, these are like terms. And I claim that I have 2 like terms. Can you spot them in the numerator? Here I have 5 to the k plus 1, and here I have 4 copies of 5 to the k plus 1. If you think of that as x, you have x plus 4x. What would you normally do? You'd add the coefficients, wouldn't you? 1 plus 4 is 5. In other words, you have 5 copies of 5 to the k plus 1. So if you don't mind, I'm going to erase the rule, come to the other side here, and clean this up for you. So what is this equal to on the left-hand side? It turns out that the left-hand side that we've been working on is now equal to 5 copies of 5 to the k plus 1, because this is 1 copy plus 4 copies, 5 copies, minus 5 over 4. Now at this point, I highly recommend for most of you to pause this video and rewatch what I just said, because I'm sure I've lost about half of you, okay? What else? Well, the next thing will be, final step, how do I make the left side look like the right side? What do I need to do? Well, look at what's different. Up here, don't we have a 5 out in front? Now, is it possible for us to do that? Well, yeah, we have a 5 in common, don't we? So that 5 can be factored out. That's a GCF, greatest common factor. What would be left in parentheses? 5 to the k plus 1 minus 1. Because 5 times negative 1 is negative 5, isn't it? All over 4. So notice what we have here. The left-hand side now, in fact, does equal the right-hand side. So we have, in fact, shown by induction that our statement is true for all n. Sorry, I get a little paranoid about colors, as you can tell. All right, so that this is, in fact, the end of our proof. It is now true for all n. What makes these proofs difficult is not the process. The algorithm is basic. Find the base case, show it works. Assume it's true for the first k terms, prove it for the next term. What's difficult for students is the algebra. So if you struggle with adding fractions, combining exponents, factoring, right? These are the things that are going to trip you up, not only in pre-calc, but in calculus. So it's always worth it to go back, find some resources. If you ever have questions about where to find resources, you can email me or talk to me in person in my office. I would love to help you, but you gotta get those foundational skills really, really down pat if you're moving on. All right, so it's up to you now. Go practice. I'll see you next time. Math's not a spectator sport.